So let's start off. Does anybody have any questions on chapter 6 before we go on? Any questions on anything in chapter 6? Friction, circular motion. If not, you could ask them tomorrow as well. So you don't have to try and force yourself to come up with something. All right. So tomorrow in lab, we've got all day to answer any questions you want. Ideally, if you have time, you would take a practice test before then on chapters 1 through 4 just to see where you're at. But you could do that this weekend or whatever. You've got a quiz Monday on everything in chapter 6. And so you could do the practice test whenever you want, but you don't want to let too far go. Too many more weeks go before you check your reasoning on chapters 1 through 4 and see if you get it. So at least sometime before Monday, you should take that practice test. That said, if you want to study your butt off on chapter 6 tomorrow in lab, that's also fine. So, or if you're just finishing up chapter 5 and you want to finish chapter 5 and then start chapter 6 and try and your goal should be to have all the chapter 6 work done by Sunday, and we've got lab tomorrow as our catch up. So for once, we actually have we kind of have a breather for once in the schedule. It looks like we might as well just plow ahead into chapter 7, and we could do chapter 6 questions tomorrow if you do have them. So let's go ahead. Ooh, exciting, exciting. Volume 2 of the workbook. All right. So those of you that had me for 110, let's see, we're here. All right, so we're finally into volume 2. So page 3 of that. Let's take a look here, maybe somewhere. Sorry, I got some Zoom windows here. All right, so work and energy. All right, and so maybe I'll just start with a brief summary on the board, but you could have page 3 open if you want as well. So let me talk a little bit about this on the whiteboard just to give you a feeling. Okay. Whoops. Let me go to speaker view. Oops. Let me get me here. And there's me. There we go. Sorry about that. All right. So got a lot of notes here. Let's first start by explaining what energy is, because if we want to understand work, we might also need to know what energy is. And maybe I'll just leave these first 2 lines up here for you. So we're going to talk about a thing called kinetic energy. Now, when I think about energy, one of the things I think about is something's ability to inflict pain. All right. So, for example, a bullet has a lot of kinetic energy, even though it has a very small mass, right? A bullet could actually kill you. And so that has a lot of energy. That's a lot of pain it could inflict. So in this case, notice despite a small mass, it has so much kinetic energy because speed is squared in here. So I should be careful here. This is 1/2 mass times speed squared. All right. So let's just make sure you know that speed. Now, we're going to talk about changes in kinetic energy. You may have even seen it on that last screenshot. But we're going to talk about changes in kinetic energy. And I just want to make you look out for something here. There's no shortcuts here. 1/2 mv squared minus 1/2 mv squared. You can't just take the velocities and subtract them and then square it. In some problems, this would actually give a correct result, but only if the initial speed is 0. So just watch out for that. Now, what does work mean? Work in physics has a strict meaning. It essentially is the change in kinetic energy. I should be careful here. This is the work energy theorem. So work relates to changes in kinetic energy. The formula we're going to use for calculating work, the strict mathematical definition of work is this. It's the integral of a force dotted with an infinitesimal displacement vector. What? This by itself is kind of scary to students at first. I'm going to show you several shortcuts so we don't have to do this. But in general, Imagine you had a drone flying in this weird snake-like pattern. At any point on the path, this could be its infinitesimal displacement vector. It's basically a small amount in the I hat, J hat, and K hat. Okay. So this, and now just to kind of make that stand out so you can see it better, I'll draw the arrows a little bit more dramatically here. So that would be that's terrible. There. So this would be a small amount of displacement. Notice you could have a different small amount of displacement over here. Or even over here, right? Maybe it's going down a lot. All right. And so we see that the infinitesimal displacement is basically just some amount in the I hat and J hat. Now, let's imagine this is a drone flying around. You could imagine that there's a force acting on it. That force might be gravity, right? That's one we all kind of, whoops, let me get a little bit lower. Okay, so we could imagine at any point on here, there's a force in some complicated way. It relates to the displacement. And so the idea is, if I wanted to find the work done by gravity, or this force pointing straight down, as the drone flies around, what I could do is I could add up all these little contributions from all the different possible ds vectors. And remember, that's essentially what an integral is. It's a sum, right? You're adding up tiny, tiny little pieces. You add up all these contributions, and notice you have to take the dot product before you do that. In practice, this is much easier than trying to figure out how to do that mathematically. In practice, we can figure out the work done by just taking the x component and integrating it by dx. Then you add to that the y component times dy plus, sorry to get it in here, it's ugly right now. I've got to erase this picture just so I have room. In practice, rather than doing that ugly pictorial thing, in practice, you could just take the I hat part of this and the I hat part of the displacement. Well, that's dx. The J hat part of this and the K hat part. And you could do this integral. These start to look a lot less scary because you don't have to do the dot product first. So what you could do is you could take the force, split it up. So for example, our last problem where there was some, the force in the x was 0, the force in the z was 0, there was only a force in the y direction there, negative j hat. And so we could just do this integral, and that's already a lot easier, right? And where things get even crazier is this. We can do some tricks when there's a constant force. So this is how you would handle any force. If constant, there's a couple of ways we can handle this without having to do all this work. If it's constant, we could actually say the work done by a force is equal to F dotted with the displacement vector, which usually ends up being F d cosine of some angle. All right. Remember, a dot product is AB cosine or FR cosine or whatever. So this is a cool trick that we can use if the force is constant. Another thing that you could do, you could actually take the amount of force that's parallel to the displacement and multiply it by the distance traveled. Or you could take the full force and multiply by the displacement that's parallel. So these are some different tricks. Remember, what does the dot product do? The dot product is a measure of how parallel two vectors are. So that's where the statement parallel comes in. Now, this is a lot of words here, and it's not going to mean much until we calculate something. So maybe let's look, let me just show you some calculations in the workbook and just walk you through it. But I guess, oh, and let me say this last fundamental thing. Work done is basically, again, it's a measure of change in kinetic energy. And sometimes I use delta K, sometimes I use delta KE. I apologize for that. In this case, if work is positive, it tends to speed up an object. If work is negative, it tends to slow it down. Now, there's going to be times when we have multiple forces and some are doing positive work, some are doing negative work, but in the end, one of them might win. And so the net work could be positive or negative. So even though a force does positive or negative work, that doesn't mean there's positive or negative net work. Okay. Also, okay, so there's a picture of this one. This is kind of the integral I was just telling you about. There's a couple of different ways to do it. And then just a second here. Where did I want to mention this, and then I'll talk about the derivation. You may notice already today I've switched back and forth between distance and displacement, and I'm going to end up doing that quite often. To be clear, work relates to displacement. However, for an object that's basically moving in one direction, we get displacement is distance times direction, or distance times some unit vector. So for most of the problems that we're going to do, at least for a little while, we're going to talk about objects moving in one direction. But strictly speaking, we need to use displacement when we're doing work calculations, not just distance. All right. The change is legal if it doesn't reverse directions. All right. Now, if you're curious where this work energy theorem comes from, here's the derivation. To be honest, we are not going to use this derivation. We're going to use the result of it. So I don't expect you to have this derivation memorized and show it to me on a test day, but it can be kind of useful to see where this comes from. So let's walk through it really quick. So that's the definition, right? Here, I could take a force, and just for right now, if we're in 1D motion, I get a force in the I hat, and then ds becomes just dx in the I hat. I hat dot I hat, just give me a second. This I hat dotted with the other I hat, that's equal to 1, right? Any unit vector dotted with itself is 1. Now what I do is I replace f sub x with mass times a sub x. So I'm assuming mass is constant for this problem, but this should still work. Okay, and so when I do that, this is the acceleration. That's ma. Force equals ma. And now this is a subtle step. This was weird. I remember when I learned it. But if you have two differentials, you can actually switch the order of them. This is totally legal. Okay, so if you have two tiny quantities, there's no issue with switching the order of these two inside like that. And so as a result, now you may not feel comfortable, but that's fine. We can worry about that later. The fact is we get some kind of mv integrated times dv. Well, there you're going to get a 1/2 mv squared. So if you're wondering where we get this work equals delta k, and why did they decide to call kinetic energy 1/2 mv squared? Why did they call it 2/3 mv cubed, right? Where do we get this 1/2 mv squared from? It comes right here in this calculus from this definition of work, okay? All right. So that's that. All right, let's look at some examples now. Let's start with the easy one. Oh, go ahead. Question in the chat. Yes, that is correct. So you could do that with differentials. You can't do that. Yeah, we could talk about when that's applicable later, like but you could do a web search for when you could switch differentials, right? Total versus partial versus inside, outside, whatever. Okay. All right. Yep. So let's start with some practical stuff. That's all pie in the sky where the theory comes from. At some point, we need to get down to work and get some calculations done. So here we go. For any constant force, we could use this shortcut. Again, d is distance traveled. I'm assuming it's going in the same direction and not changing direction. All right. So if we have a block, and let's say we have some tension, it's 12 newtons in this direction, this angle. We plug in these numbers. We get this cosine of 10 degrees in there. And notice you get positive 35.5 joules. This seems reasonable. If I pull the block almost to the right and it moves to the right, that force of tension was probably helping to speed it up. Now, we don't use these units of Newton meters. We're going to use units of joules. All right. So joules is a real gem of a unit. Okay. Now, I just want to show you, you could actually do this using the dot product. So if you wanted to see how that works out and why this equation is legal, let's look at this one right here, redoing this example. First, I'm going to split up the tension into X parts and Y parts. So I hat and J hat parts. There's the tension. I could do the same thing with the displacement vector, right? I split it into I hat and J hat parts. Now I can simply say the work done by tension is take the X part with the X displacement, the Y part with the Y displacement, T part, Z part, Z. Well, in this case, this is the only non-zero term because there's no displacement in the J hat, excuse me, or K hat, and we get back the same exact result. So this is 2 ways of showing you that. I'm going to pause and see if there's any questions. I'm going to leave this on the screen. Any questions about those first 2 examples?
Yes.
Yeah, go for it.
If you were to change the coordinate system, making it go the other way, would the work change?
Yes, so work can be negative. So now the coordinate system shouldn't change anything. So think about this, and I think this is your question. So remember, physics shouldn't depend on the coordinate system. Let's say you said this way was positive, then positive I hat. This would have a negative I hat, but so too would this, right? And so minus times a minus, you'd still get positive work done. Is that cool?
Yeah, so it wouldn't really affect, it would like just change the signs, but not the work itself.
Signs of the force, and it would change the signs of the displacement, but it wouldn't change the physically meaningful quantity of work. Which again, work is a scalar, right? It relates to the amount of energy change of the object, the amount that the thing changes. That's a good question. Others? All right. So let's try, before we get on to non-constant, let's just make sure we can get this one. So I'm going to start with this problem right here. So I'm going to get it drawn up on my whiteboard for just a second. And I tend to go through this first example pretty slowly. So if I'm going too slowly for you, there's always the solution as well, okay? So let's try and learn about this one through an example. So I'm just drawing it up here, and then I'll share my whiteboard in a minute. (7.1) Okay. So we know this thing is going to go up the hill. And then just a subtle point here. Strictly speaking, we should go from the center of mass to the center of mass to show this block. So that distance is L. Now, I hope you agree, going from the front of the block to the front of the block is also equal to L in this case. If you're going on a circular path, that's not true anymore. Okay, so I'm foreshadowing chapter 8 here. But for now, as long as you're talking about objects moving in a straight line, we could go from the front of the block to the front of the block, or the back of the block to the back, or the middle to the middle. Anything will work out just fine. All right. So it's okay if this picture isn't exactly the same as the one in the book. All right, so I think we're supposed to do an FBD first up, right? So part A is get the FBD. What's one force acting on this?
Forgot the force to the right.
Okay. There's F. What else?
Normal force.
Normal force. Which way is that? Kind of describe it.
Perpendicular to the ramp.
I like that. What else?
Gravity down.
What else?
Do we have friction? Because it says mu is not, or it says it's not 0. Yeah.
So then we do have friction. Which way is that?
So it's going up the plane, then friction is down the plane.
Yeah, the block moves up the plane, so friction must point down the plane. Good. And I think that's all of our forces. All right. Is there any indication of whether or not it's accelerating?
It says magnitude of acceleration due to gravity is g, so yes.
Now, careful. All that's saying is G is G. Right?
Oh.
This is not right. This is not in free fall. So the magnitude of this block's acceleration is not G. Right? So another thing that this is saying is basically we are on planet Earth. That's what that line is saying in another weird way. Right? It's just saying, hey, if you drop something in free fall, the free fall acceleration would be G. Aha, we must be on planet Earth. Yeah. So anything else? Do you see anything else explicitly stating that it's accelerating?
So it does say that mu is the kinetic coefficient, so not static. That would mean it's moving, but not necessarily accelerating.
Exactly. We don't know. So here's the deal. If you don't know if it's accelerating, what is the safest approach to assess it? Should we assume A is 0, or should we assume A is some other number? What do you think?
Assume it's 0.
If you assume it's 0, it had better be 0 or all your work is wrong. If you assume it's non-zero and it's some number, you include the possibility that A could also equal 0. So if you're unsure at a problem, the safer bet is to assume A is just something. Are you okay with that? It's subtle. If it doesn't say that it's accelerating, assume it is until you know otherwise. It's sort of like with a frictional problem, right? If we don't know if something's on the verge of slipping or not, we don't assume it is until we know otherwise. So, is that good on that, Gongon?
Yeah.
Yeah. So now here's the other thing. You could argue, dude, how do we know you didn't draw acceleration the wrong way? What if this was started at 10 meters per second, and then by the time you get up here, it's only 9 meters per second? That's totally plausible, right? You could push on it, but it might slow down. Maybe it was moving. I would argue this is still a good assumption, because later on we could say, well, you expect a negative value for the term A. And so this handles whether A is positive, negative, or 0 by making this assumption. All right, enough said. We could do a little math. I think, how would you choose to split up these coordinates if you wanted to learn about the normal force? Part B asks us to learn about the normal force. Would you use a standard XY or would you use a rotated XY? What do you think?
Rotated?
I would probably go rotated. So just to show that, do I need to split up any other forces?
The force.
Yeah. Are there other ways to correctly do this? You bet. But this is one correct way. And then if this is theta, if that's theta, what's this angle?
90 minus theta?
This angle.
Theta?
Theta. What's this angle?
90 minus. Oh, yes.
That's 90 minus. Here's the 90. Here's theta. So this must be 90. So that leaves what for this one?
Theta.
Right here. That's theta. Okay. So we got our thetas. Iota theta. All right. And so I think you could get the normal force from this. Let's see. In this case, I hope you agree that the normal force is mg. Let's see. What's this component? Sine or cosine?
Cosine.
And then this one over here.
Sine.
Sine. So it's going to be mg cos plus f sine. I'm just going to double check this when I got it. All right. The idea is the ups have to equal the downs. Well, this is one of them. And this is one of them. So yeah, that looks pretty good. Everybody okay with how I got the normal force? C asks for the frictional force. What should we use for the frictional force? Oh, there's somebody in the chat here. Let me get that. Okay. What's this? Oh, go
question.
ahead.
For
Yeah.
B, why don't we have mass times acceleration?
In this case, what's the, okay, you could be saying, let me write this another way. I could write mass times acceleration in the y direction. But what is the acceleration this way? You see it?
Sorry, I was looking. I thought we were doing the X. That was my bad.
Oh, yeah, I was doing the verticals. Yeah, so I chose to do the y's first. And so if this goes to 0,
And yeah, normal force equals then. You got it. See it.
then I move the two negatives to the other side. Yep. And you're good, right? Okay. So now in this case, what frictional condition applies?
Kinetic.
Kinetic?
Kinetic. Finally, an easy one, right? The problems with kinetic friction, you're like, it's obvious it's moving relative to the surface. So do you agree? We know F has been applied. Mg is something we know. We know about the normal force. We know about all the different forces in the problem. In theory, if I gave you the mass, G, mu, and the angle, we could punch in numbers. We know all the different forces. Okay, so check this out. Part D says, get the work done by the force F, capital F. Notice it's useful to keep track of lowercase and capital, right? Well, this is F D cosine of some angle. How can I use that? It's a constant force. This is the constant force work equation. Now, you may not know why we're doing this. I'll explain after we do the actual how you do it, and then I'll tell you why we're doing it this way. So just trust me for now. Let's get a feeling for how to do this. Now, a thing that I like to do that is not required, but I highly advise it, at least when you're beginning, is instead of just trusting you could read this picture, draw a mini picture beneath. Show the force itself, then show the displacement as well. The displacement for this one is this away, right? And its length is L. So the distance is L, the displacement is L this away. Well, and we already know this angle in here is supposed to be theta. It's a little small for me to write, so I'm going to redraw. That is L. So in this case, it's pretty obvious to me that the angle is theta, right? It looks exactly like that, right? Same angle. If you want to do a parallel line theorem, you could say if this is theta, this is also theta. So this one's pretty quick. It's just F L cosine of theta. like that. Okay. Now, any questions about that? This is not required, but I think it helps you understand what angle you should plug in. You'll see that in the very next one, the angle is not always theta. That's where I'm trying to watch out for. Next. I believe the next one was get the work done by gravity. Is that right? I want to check. Sorry, I just got to read the question again. Okay, get the work done by gravity. All right, this one is a little bit trickier. So I'm going to lower this down here. E, work done by mg. Well, the force is mg. The distance is still L. And then I still need to figure out the angle, right? So let's draw our picture to figure out the angle. And once you get used to doing that, it's golden. That is the displacement, L in that direction. Here is mg. What's the angle?
Is it theta plus 90?
Yeah, I think so. Because look, isn't this? Yeah. So the angle between, in this case, is not theta. It's actually 90 plus theta. And that's what I was warning you about. If you just start blindly plugging in theta all the time, you end up getting it wrong about half the time. All right. Now, it turns out there's a trig identity for this. And to save us time, me drawing the pictures, I've drawn it in the solutions. So I'm going to cheat and go to the solutions. Notice the trig wheel here. So cosine of 90 minus theta, I believe that's what were we supposed to do? Cosine of 90 minus theta, right? That is essentially this value down here, right? The x component. Well, notice that's also related to sine of theta, but in the negative direction. So if you recall, these cosine is positive in the first quadrant, cosine is negative in the second quadrant. So if you just take sine of theta, you're not going to get it right. So that's how I got negative sine theta right here. Cosine, oh, let me see if it's just right here down on the page, just a smidge. There it is. So that's this trig identity right here. If you have trouble seeing it, who cares? You could Google that. That's not important. But for now, I just want to show you that this could be, this is really ugly to work with. It's a lot prettier if I say this becomes negative sine theta. Whoa, wait a minute. You're telling me after all this is done, I need some space, so I'm going to erase this figure. I know you have it in the solutions end of YouTube. We said it's equal to negative mgl sine theta. It says work is negative. Does that seem reasonable? Let's think.
Well, gravity's trying to pull it down.
So
right?
it's an, yeah, that makes
yeah.
sense, right? And so that's how you check these minus signs. You're like, well, let me think. The force is pushing up. That should be a positive work. Mg is trying to hold it back. So that's going to be a negative work. Got it. This looks cool. Now, I'm going to show you one other way. I know this seems crazy. I like to show people every possible way I could think of to calculate this and then let them decide what they want to use. This might be a smarter way to do it right here. Give me just a sec. So notice in this case, this is the component of gravity downhill. Mg sine theta there. Notice the angle between is 180. So you'd get mg times, mg sine theta times L times cosine of 180. And what's cosine of 180? Take a guess.
-1.
-1.
-1. And so we get exactly the same result. We see this minus sign pops out this way too. So if you like this style better, this is something you could always do. You could always just say, okay, get the component that's parallel to displacement. Strictly speaking, I would say this is anti-parallel. It's parallel, it's on the same line, but it's going the opposite direction. So sometimes you'll hear me say the word anti-parallel. So parallel, anti-parallel, whatever. Got it. All right, so there's that one, and that explains this minus sign. So just to save a little bit of space, and I can't help it, I like to bring this up right now. So for me, after a hard day of doing work, it's nice to have a little MGD. If this helps you remember it, I don't know why, but it's funny. I didn't even drink when I was in college, but I actually didn't start drinking until I started working at Allen Hancock College. For real. Correlation? Anyways, but I like to remember MGD is a work term. So if this helps you remember it, cool. If it doesn't, I'm sorry I wasted your time. But MGDs, right? If you're doing a lot of work, you're going to have a lot of MGDs, Miller Genuine Draft. All right. Next, let's get to the next part. F. Is that the normal force? Work done by the normal force? Yes, work done by the normal force, I think, is part. Oh, work done by friction. I apologize. Sorry about that. Now here, I'm going to cheat a little bit. F is going to be some really long equation, okay? Really long equation. So I'm just going to write F for right now. D, the distance it moves, is still L. And then what's the angle I need? I'm going to draw my picture in a minute, but you could think what angle I need. That's the displacement, distance L up the ramp. Sorry. Distance L up the ramp is the displacement. Friction's this way. What's the angle in this case?
180.
180. That's the Dua Lipa theorem. Oh my gosh. I don't know what's worse. In this class, I referenced Dua Lipa. The last one I referenced One Direction. I mentioned Harry Styles. Now I mentioned both in this class. So clearly you guys are the worst class. You're getting punished with these horrible, horrible references. My apologies. Whatever. This is what happens when your daughters make you listen to music. So out of all this, you get what's cosine of 180? Negative FL. So the work done by friction is that. Technically, this is not correct according to what the question asked. It said in terms of mg's and all that, but I hope you agree we could just shove in this crap up here and get it in the right form. So I'm going to stop there for the sake of this whiteboard. And I hope you see the merits of drawing this little picture here when you're trying to figure out the angle. That's all that's for. Now, we need the work done by the normal force, I hope. Because there's only 4 forces. Man. Wait, I just wrote MG. I'm still cringing over my references here. Sorry, I'll try and reference only 70s pop light rock after this. That way you feel more comfortable. Okay. What's the work done? Go ahead.
In the workbook, it has a, I don't know if I missed it, but it has a little bit different. It's worked out a little different, or in the solutions. Yeah,
it's going to look a little bit different because I just didn't plug in all the junk.
Oh, yeah, okay.
Remember, like this, oh, crap, I got to plug in this and this. And so it's going to be all that shoved in there. It's going to be,
right.
You know what I'm saying?
All right.
And so I'm confident you could do that. You could do that later. All right. Good question, though. Thanks for checking. Others? All right. So now let's do the work done by the normal force. It's the normal force times the displacement times cosine of what angle?
90?
90.
Oh.
So I'm going to draw the picture so we can see it. Sorry if that's wasting your time. Remember, the length is up the incline, so that's the displacement. The normal force points this way, perpendicular to the plane. Notice, what's cosine of 90 degrees?
0.
0. Think about it. The work equation, the definition came from a dot product. Dot products measure how parallel things are. In this case, something that's perpendicular is not parallel at all. It does no work. Now, before you get kind of frizzled by this, maybe you even haven't had time to realize this makes people feel uncomfortable sometimes. You're like, well, wait, doesn't the normal force do anything? Obviously, yes. If there was no normal force, it would fall right through the floor. And if there was no normal force, there wouldn't be any friction. So the normal force clearly is an integral part of this problem, but the strict mathematical definition of work given in physics says it does no work. So the force is there, it does something, it's hugely important, but it does no work. So what are we saying? We're saying the normal force doesn't tend to speed up or slow down the block. And that is reasonable. Look, this is saying, hey, I'm Switzerland here. I'm going this way. I'm just going to do what I want. And you guys could push left and right all you want. I'm not having any part of this. So I'm not going to do anything to change the speed of the block. I'm just going to hold it up. All right. Anyways, that's the normal force. All right. So sweet. Now, after all this, I just want to point out part, what is the next part? Determine the speed. Aha, look at the wording in part H. Now we clearly know it was accelerating. It basically does no work in the physics sense. Absolutely right, Gong. That doesn't mean it's not important. It just happens to do no work in this mathematical definition. Where does speed show up? Does anybody have an idea? How can I get speed involved?
When you break down the force part of it?
That might lead to it, but there's a faster way and so what you're thinking of certainly is not the way I'm thinking of. It's faster. That doesn't mean you're wrong. I just don't know. Any other ideas?
Well, work is delta K, right?
Aha! 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 Work equals delta K. Now, I'm going to be clear here. The net work equals delta K. That's pretty sloppy, so I'm going to rewrite that in. The network. So think about this. If you take these four work terms and add them up, you would get the net work. That's equal to the change in kinetic energy. That's 1/2 mv final squared minus 1/2 mv initial squared. And remember, you can't just say v final minus v initial and then square it. We are told this thing starts from rest. Starts from rest means this goes to 0. If that goes to 0, I could solve for the final speed. I multiply by 2, I divide by m, I take a square root, I do some algebra, I shift some crap around, I keep talking while I'm trying to screen share just to kill time, and then I get this result. Now, you could check this later, and you could see this is probably one worth checking at home. Okay, so, well, I guess you are at home. That's kind of weird. I snapped back in the classroom mode. But yeah, check this sometime later, not right now. And then here are some things that we should notice out of this. If you have force components perpendicular to the direction of travel, they do no work. Force components directed opposite the direction of motion do negative work. So we saw that you could have negative work from friction and gravity, and it's possible they could do, I don't know, Is it possible friction could ever do positive work, or is friction always going to be against you? What do you think? So that's it for this problem. Any questions on that before we go to my next one? It's just math. Okay. Is it possible friction could ever do positive work, or is it always going to do negative work, right? Generally tends to be opposite your motion, right? What do you think?
I don't know if this is a good example, but maybe like a car where you're using friction to push backwards to go forwards. I don't know.
That's tricky. Let me ask you this. The point of contact with the road, right? That's at rest. So how much is it displacing relative to the road?
Right. Yeah. It would
so
be doing no work.
In
that case.
But then why does the car go, right?
Right.
So so this foreshadows. So that's a complicated one because a lot of issues come up and then we have to talk about this. So let's ignore the car for right now. You are probably right that the car, right? Because friction's what makes the car go forwards. But let's try to give an example where it's not something with stuff moving in circles. Can you think of one like that?
What about to generate heat? I'm thinking kind of maybe chemistry kind of maybe.
So yeah, it turns out this is actually related to that. Heat is energy. And so you could talk about thermal energy. And so, okay. Yes, quite possibly. And you're probably right there. This is awesome. Very cool ideas. I was thinking of something much simpler. So I'm going to go ahead and do it now because both of you answered very well. And those are some cool examples. Whoops, not that one, this one. Oh, there's somebody here. Not sure what you mean, Gongon. You might be on it, Terry, but just look at this. Look at 7.2 on the next page. This is a much simpler problem that we've already done that's pretty straightforward. Take a second to look at this. 7.2. I'm going to erase the board while you guys kind of look at that and think about it. Those are great ideas that you both brought up. Gongon, I just didn't understand yours, that's all. It's related, certainly. I just don't know what you meant, that's all. All right. You tell me. For the first block, the upper block, does friction do positive, negative, or no work?
No work.
Positive.
Well, let me ask you this. Let's do an FPD. There's a normal force. There's mg. Which way is friction? On the upper block.
Forward.
To the right.
To the right. Which way is this upper block being displaced?
To the right.
To the right. Is the work positive or negative?
Positive.
There's a simple example. And this actually is very similar to the car tire one, right? So what we see, let's keep going. How about now remember, there's no friction down here. There's no friction at the bottom. No friction on the floor. Negligible anyways. So does friction do positive, negative, or no work on the bottom block?
No friction. No work.
There's friction back, right? Maybe if I label this N12 and this is friction 1-2, you'll see it. This is friction 1-2. It's the action-reaction pair. And so it does, Jacob, you're on it. Okay, so look, this one's negative, but now think, it's the same force, the same displacement, the same angles. The network is 0. And so when you're driving a car, right, you're basically doing some work forwards on the car, some works backwards on the earth, and there's no network. So it's a little bit goofy. All right, we just don't, anyways, let's leave it at that.
So no network on a system means that the system is like still, it doesn't move.
No. Well, let me put it this way. If there's no network, the energy theorem is work equals change in kinetic energy. So if there's no work, there's no change in your. If work equals 0, let me just write this explicitly. If work equals 0, delta K is equal to 0. If your kinetic energy isn't changing, what else isn't changing?
Speed.
Speed. How about I just write V because I'm so slow? So you could be moving with constant speed, right? Does that make sense, Alonzo?
Yeah.
Yeah. So just because work is equal to 0 doesn't mean you're motionless. Can you give me an example of something that's moving with constant speed that has 0 work that we've been talking about for about a week?
Maybe an ice cube.
Say again?
An ice cube?
Okay, an ice cube sliding across a lake. True. Think about it. If I spin this fast enough, it's at constant speed, right? At any second in time, it's moving this way. What direction does the string pull?
Towards the center.
Yeah, perpendicular to displacement, right? So if my so sorry, it's hard to draw here. Right? If the displacement is this way and the string is this way, at any point in the motion, the displacement and the string form a right angle. The tension does no work. And if you're spinning this, there's a case where it's a very complicated problem. Tension is a huge deal, but it does no work. This motivates me to bring up the point, why are we caring about this at all? Okay. So why should we care? Here's why. In this case, we've done basically 3 techniques that involve physics: kinematics, forces, and now this new one, work equals delta K. We have 3 physics tools in our toolbox, and each one serves a purpose. This does not solve every problem easily. Neither does this. Neither does this. However, in certain situations, some of these are the easiest. And so it's like grabbing for a screwdriver versus a wrench, right? They have different purposes. They serve different they're different tools. They serve different purposes. Let me leave it at that. And so you may have noticed, and let me check the chat here. Yeah, true. That's true too, Gagan. And so what we see, however, is that there's certain times when this will get the job done fastest, this and this. For example, look at 7.1. I just want to point something out. I'm going to share a screen really quick. Look at 7.1 on my screen when I bring it back up here. Look at this. You probably could do this problem. If what we were trying to do is get the final speed of the block, couldn't you first do forces, then do kinematics? For example, you could do forces and get A. You could do sum of forces, and you could get MA. From that, you could say, well, I know V squared is equal to V initial squared plus 2A delta X. And that would work. But I just want to point out what we did was we did forces and work. And that's another way. And what we see is once you've done a few of these, there are going to be some shortcut tricks. And that's basically chapter 8. We're going to learn some shortcuts for this one. We'll learn that we don't even need to calculate that one. That'll save us some time. And we're going to learn a shortcut for this one. And basically this one was pretty easy to begin with. And so it turns out if you use this work equals delta K, you don't have to figure out the acceleration. Did you notice that? In general, there are going to be classes of problems where we don't need acceleration and we only need speed. If that's the case, this might be the equation to use. So when we're doing problems that talk about speed, this is pretty useful. This one talks about acceleration. And what appears in the kinematics equation that doesn't appear in either of these other two?
Time.
Time. So even though this isn't, a be all end all, on a final exam, when you get a problem, you don't know what chapter it's from. How are you going to know what to do? You read the words, and let's say the question asks for speed. I don't guarantee this tool will get the job done, but that's probably the one I would try first because it usually helps. If I'm trying to get an acceleration, I would not do this. I would probably do forces or kinematics. Now, obviously, there's some overlap. Displacement is in both of these. Velocity is basically related to all of these. Again, I guess not really in here unless you use this as well. So, okay, enough said. Basically, we are learning another tool. And in chapter 8, it gets really easy to solve for speed if we learn this technique. That's why we're doing this. Got it? It's just another way of analyzing motion. All right. Let's see where we're at here. All right. So we've kind of talked about this one. Now, in this case, question, I think I left part of this for you to solve on your own. That's fine. Question 7.3 and 7.4. Those are kind of, this is another conceptual one, and it's got zombies and nanobots and chemicals. I mean, come on, it's psychotropic chemicals too. So clearly this is a good question for you to do outside of class. But those are very similar to what we just did. Before we go on, I'm going to skip to this one and then we'll take our break. So let's look at 7.5. You have a car, mass M. You're driving on a banked curve. You've got speed V, radius R. The curve is angled. Okay. Car is driving at the maximum speed possible without sliding to the outside of the track. These are the coefficients. Okay, so notice I'm explicitly stating don't look at the solution for this one. Okay, in this case, the car is going to drive halfway around the track. So in theory, we could get the distance, blah, blah, blah. What is the work done by the normal force? Work done by gravity, work done by friction. How would you approach this problem? What do you think?
Try and draw an FBD first.
Okay, I'll draw an FBD here. There's a normal force. So I'm assuming, let's just make clear here, we're talking about a car. That's supposed to be the car. It's driving around in a circle on a banked curve. So that's supposed to be the curve. This is the rear view. This sounds like a really bad Hitchcock movie. Rear view FBD. Anyways, man. And I've even been sparing you guys today. There's been a bunch more references I haven't made. Oh, anyways. There's a normal force here, mg. Okay. What else do we have here in this FBD? Anything?
The friction.
We got friction.
Friction, which way? Go for it, Alonzo. What do you think?
I was thinking up the plane, but I'm rereading it to see if it's the minimum speed or the maximum speed.
Maximum speed. So what does that tell you?
Down the plane.
Nice. So maximum speed, you tend to slide to the outside. So maybe we expect something that looks like this, and there's friction. All right. So how do I get the work done by the normal force in this case?
So we need to, do we know the displacement? It's half, right?
Halfway
So-
around the circle.
Okay.
So that would be pi r, right?
Right. Yeah. Okay.
What's the angle? It would help to draw it, right? The normal force is this way. What direction is this car moving at this instant in time?
Up the plane?
Nope. It's not sliding to the outside of the track.
Mm.
To the right?
Nope. Think about this picture here. Maybe I should draw the top view. Remember how I said sometimes the top view can help?
Is it towards the left inside?
Nope.
So into the page, isn't it?
Into the page, suckers. Right? The car, we're looking at the rear of the car. The car is driving into the curve that we can't, right? So what's the angle between into the page and up and to the left? It rhymes with 90.
90.
90?
Yes, very good. Very good. So what's the work done by the normal force?
0.
0.
Wait a minute. What's the work done by mg? That's the velocity. What's the angle?
Is that 90 plus theta?
No, it's 90.
Oh.
That's the answers. They're all 0. Look at it. Let me show you here. Sneaky, right? All right. So here's what the forces look like if I could. Oh, this is hard to hold this. Yeah. And so that's the thing is sometimes physics, you have to kind of think and stretch your brain. The idea is this is what the forces look like. The velocity is at right angles to all of them. Sorry, this is extremely difficult to hear, right? Now I'm losing it, right? Like that. Sorry, this is getting there. Oh my gosh, this is hard.
So is the blue marker the back of the car?
The blue marker is the velocity. You're going around the turn, right?
Oh.
Yeah. Sneaky, isn't it? So I realized this the other day. I'm like, well, the other day, I don't know how many years ago, but the idea is just that, oh, I could totally mess with my students. Think about it. It's exactly the same as the ball on the string that I just told you the answer to, right? Whoops.
Oh, yeah. That makes
So
sense.
it's very similar to this, right? So now the displacement is going this way. And you can see it. It's perpendicular, right? And so mg is down this way, perpendicular. So the conical pendulum, this little one, whoops. mg and tension are both perpendicular. Neither one does any work. So you probably wouldn't want to analyze a banked curve or a conical pendulum with a work equation, right? Because everything's 0. You can't solve for anything. It's a pointless analysis model. It's absolutely legitimate. It's absolutely correct, but it's worthless. It doesn't help you learn anything. So, but it's still valid. And that's what that was all about. Okay. It's a trick question. So if I could, this is not bad, right? It's just like the Earth, right? The Earth is being pulled toward the center of its orbit by gravity from the sun. The Earth is moving with roughly constant speed in our orbit because it's basically circular. So now it doesn't mean these forces aren't doing anything. The velocity changes direction, but speed is not changing. We were told in this problem, right? It was a car driving with speed v. When you say that, when I say driving with speed v, that implies constant speed v. And so this is nothing is inconsistent here. Nothing is anyways, I'll leave it. I was going to do a Big Lebowski reference, but I already swear enough as it is. All right. So this is a good time to take a break. So let's come back at 6. Wait. Yeah, let's come back at 6 p.m. on May 7th. Or how about just 10 minutes from now? Isn't that about when the semester ends? Maybe I should say May 21st. All right. 10-minute break. If you have questions, I'm sitting here for a sec. I'm going to go get some water. Still got a minute, but if you have any questions, I'm here. Has anybody ever watched the live streams or no?
Yeah, I watch them after lecture all the time.
That's cool. They help out a little.
Yeah, they're good to review when you're doing homework and like you need like your explanations.
I gotcha. Yeah. Hopefully we're doing some problems that are on your required list, so we're knocking some of them out, but I have no idea how that all works out. All right. Let's go ahead and get back into it now. And we've talked quite a bit about non-constant forces and how you could do a work equation for that. So now I want to talk about, I think we talked about constant forces. Now I want to talk about non-constant. Sorry for misspeaking there. All right, so let's go back to here. Okay, so this is a good one to do when our brains are fresh. So it turns out, and let me just get the whole thing on the screen here just for a second. Okay, I think that's it, right? Yeah. Okay. So I'm going to say some boring phrases in a minute, but you just got to stay focused because this is a tricky one. Okay, this right there is the general definition of work. If we restrict ourselves to a force in the x direction only, so for a non-constant force, x direction, the force becomes F subscript x in the I hat. Now, ds, we might as well just say you're moving in the I hat as well, right? So instead of trying to figure out some complicated thing, and again, if you're wondering what happened to the I hats in that last one, give me just a second. I hat dot I hat equals what?
1.
1. Okay, so that's going to equal 1, any unit vector dotted with itself. Pizza hat dot pizza hat equals 1. And so, okay, so this in practice is the equation we're going to use for figuring out work for non-constant forces. Now, the next piece of this one, the most obvious thing to attack is a spring. Springs are incredibly useful, and so much of matter can be modeled as a spring, at least to a first approximation. Okay, and now I want to point out some complicated things. Look at this equation. 1, 2, 3 times. They are slightly different, and we need to explain those subtle differences here. Let's start with the most general definition. This is always true. Always. This is the force due to a spring. It's negative K. K is just a constant. It relates to the stiffness of the spring. A slinky is a spring, but it's just a very weak spring. It has a small K. The shocks on your car have a spring in it. That's much stiffer than a slinky that has a large value of K. Okay, so K is just a number that talks about how stiff the spring is or how stretchy it is, whichever way you want to think about it. Delta X is the displacement of the spring from the unstretched position. Every word in that is precious. There is no simpler way to say it. Technically, it's a displacement. And it's not just any displacement, it's a displacement from the unstretched position. So let's look at this picture right here. Okay, and let me clear out some annotations so we've got less going on here. This is X unstretched. I'm going to call that X un. All right. Over here, look at delta X, right? If this is X final, and all right, so if I go to the center of the block, right? So what I did is I put this at the center of the block, but the spring, because we're in a horizontal, right? Really, the spring is stretched the same amount as what the block moved, right? So that's not, there's nothing wrong there by using the center of the block. That's common. All right. In this case, delta X in this equation is X final minus X initial, which is X un. Now, if we set the unstretched position to 0, that's going to get rid of the delta. So usually when you're doing spring problems, the first thing you do is figure out the unstretched position. Once you know the unstretched position, you set that equal to 0 so that you don't have to keep writing the delta X, and then we just have X here. And that makes things a lot easier for us. So you can choose any coordinate system you want, but this is the obvious one to choose for springs because X is a lot easier than delta X all the time. Notice in this equation, the force is a vector, X is a vector, it's the position vector, and it could be positive or negative. Does this equation make sense? Sure. If you stretch it to the right, the force is to the left. If you compress it, some springs can be compressed. So if you compress it, the force would be this way when the displacement is this way. So if you displace it, okay, so this seems reasonable why that minus sign is there. However, in free body diagrams, we don't usually draw the force vector, or excuse me, we don't really write the force vector. We write the force magnitude. So notice this one has no minus signs. X is a distance, and everything in here is positive. So be careful when you're reading your book. Okay, so if you haven't started reading the textbook, you really should. But when we're doing FBDs, the KX is the size of it, and that will always be positive. The arrow will tell you whether it's plus or minus. So as you read about springs, pay close attention to vectors versus magnitudes like everything else in a physics book. Any questions just about these three equations right here, here, and here? Hopefully that makes sense, the subtle differences. I'll try to always make clear whether I'm talking about a magnitude or a vector, but if you're not sure, ask. Just unmute and say, dude, I don't know what's up. All right. So let's start with part A here. All right. Let's start with part A. So I'm going to do this on the whiteboard because it's a little easier for me. Okay. And this is 7.6 on page 6, I believe. Yeah. Okay. So I'm just going to check the newtons, the units. In this case, the units of F equal the units of K times the units of X. Vectors do not change the units on something. So in this case, I get newtons. Well, let's just solve this for the units of K really quick. Okay, so remember those square brackets mean something to me. This says the units of K are the units of F over the units of X, which are newtons per meter. So far, so good. So that was part A. And just to save space on the board, I'm going to now erase part A. All right, because that's pretty straightforward. So part B asks us to get the work done stretching it from 0 to 6. So I'm going to use my new equation. Now I'm going to put in the full vector here. Like that. Now again, this is normally ds, but if we're just going right and left, ds by definition is dx in the I hat. It's a small amount of length, infinitesimally small. All right, so it's a small amount of length to the right. Okay, and we could stick in the limits later, but for now, I'll just say initial and final. So now let's go in here. This is negative kx vector dotted with dx in the I hat. Now, I hope you agree that x vector could be rewritten as, let me just make a little space here, x in the I hat. All right. And so, again, this is x vector. Nothing crazy here. Again, we see that I hat dot I hat equals 1. And we get this integral. And I'm just going to put initial and final for now. It saves me time just writing initial and final. Okay. Negative kx dx. When you integrate that, I hope you agree that we get 1/2 kx. Oh, it's a minus sign. We get negative. So just maybe to highlight that minus sign, let's make it really pop out here. Remember, there was a minus sign right here, a minus sign right here, and all that came from the definition of the force in the spring. So when we do this integral, k comes out, integral of x is x squared over 2, and then I put in the limits of initial and final. So this is another one of those ones. You can't do x final minus x initial first, then square it. You got to do each term separately. All right. In this case, I believe the problem told us that k is 40, x initial was 0, and x final was 6. So I should be able to just plug those in, right?
You have to have the same units?
Nice. Watch out. I was trying to trap you by making you forget about this. K has units of newtons per meter in the problem statement. X had units of centimeters. So you better make sure you do the limits right. So this was from 0.00 meters up to 0.060 meters. We've got to do that conversion. Whoops, sorry. Let me put this down a little bit. All right. So this is a sloppy letter M. So make sure you put in the right units. This is another place where people screw up on springs all the time. A common unit for a spring is kilonewtons per meter for a heavy-duty stiff spring. And centimeters and meters get used a lot. And so you kind of always be checking your units on these. So let's see if there's anything we forgot on this part. And so notice I had to remember to do the conversion. I did the sig figs and I got negative 72 millijoules. Remember, the units are a real gem of a unit for work. It's millijoules. All right. All right. So far, so good. Whoops. I meant to hit the other button. Whoops, this one. There we go. So we have now done part A and B. So in this case, obviously we could do this with the different limits, but before we do that, let's take a guess for fun. You're going to stretch it instead of going from 0 to 6. We're now going to go from 6 to 12. Do you think it will be the same amount of work? Do you think it will be less? Do you think it'll be more? Do you think it'll be double, triple, quadruple? What do you think? What's your gut tell you? It's okay to guess and be wrong.
It would be more into, but like more negative.
Yeah, it's going to be a larger negative number. Okay. Do you think it'll be twice as much, 4 times as much, or something else? Go ahead.
I was gonna say the farther you stretch out a spring, the more it wants to pull back, right?
That's right. And so the fact that you didn't immediately answer with twice or 4 times as much is a good thing. That's what I was looking for. The short answer is, I have no clue. Let's do the math. And that was the smart thing there. So basically, if we plug it in, I ended up getting 216, which is actually 3 times the amount. Now, what some people do is they look at this equation and we see, oh, well, if you stretch it twice as far, if you go out to 12, shouldn't you get 4 times as much work done? But again, it depends on not only the final position, but also the initial position. So this is something you have to watch out for. If we go from 0 to 12 instead of 0 to 6, then sure, it would be 4 times as much. And in fact, if you add these two together, you see that it is 4 times as much. All right, whatever. Let's go back to this one now. So that's cool. That's just plug in the numbers. It's exactly the same as the last one, just a different initial and final. And the goal of this part is just to show you, don't make any assumptions, just do the work, plug in the numbers, you'll get it. All right, now here's a fun one. We're going to take this thing out here to 12 centimeters, right? And then afterwards, we're going to let it, and I should be careful. I should go right to the center here. Let's say that's 12 centimeters. And then afterwards, I'm going to let it go over here. I'm going to release it, and it'll get over to this position, 12 centimeters over here. So I hope you agree this seems reasonable if there's negligible friction. I'm assuming I said that somewhere. Did I say that? Oh, well, let's be clear here. If I didn't say that, we should add this in. Everybody say negligible friction in this problem, okay? Otherwise, it's a lot harder. Sorry about that. I should add that in. Negligible friction. Is this realistic? You bet. You could put this spring on a cart that has little wheels. And if the cart has little wheels, the friction is completely negligible. The wheels have negligible mass. They have negligible energy. So it's totally legitimate to say there are problems with negligible friction. Totally legitimate. All right. So that said, we're going to pull it over 12 centimeters. We're going to release it. Obviously, it's going to keep going. And if there's negligible friction, I hope you agree, it'll come all the way over to here. What is the work done? By the spring force as you go from positive 12 to negative 12. What's the work done?
So do we want to do a 2-stage problem here? And solve
You could,
for
or
0
you
to
could just
12
state
and-
the answer that rhymes with hero.
0.
Oh,
0.
yeah.
Why? Now, you're absolutely right, Jacob. You could do a 2-stage problem, but how do I know it's 0? Let's start by this. As you're going this way, if you release it, is the work done positive or negative as you're going this way?
Negative.
Really? If
Wait,
you
is
release it from here, aren't you moving that way?
Sorry, I got the wrong direction. Yeah.
So work here should be positive because the spring is what's causing you to go to the left. Again, we're starting here and we're releasing it. It's going to go towards the center. As soon as you cross the center, you're going to keep moving this way, but the spring is going to push the other way. I hope you agree that the work is now less than 0. This is another one of those problems. If you start at rest, your initial speed is 0. At the moment you reverse direction on the other side at -12, your speed is also 0. There's no work. There's no change in kinetic energy net because the two stages do the same amount of work, but with opposite signs. So this would be a problem that is almost worthless to use the work technique on, but it does still match up. Does that make sense, everybody?
If there was friction, would it still be net force 0?
If there was friction, the net work would still be 0. However, what would be different if there was friction in the real world?
The distance wouldn't be the same.
Exactly. So if you had a problem like this with friction, let's say this is the un. Okay. So in this case, we would expect, and let's say this distance right here to the center of the block was, say, 4 centimeters. If there was some friction, we might only go this way 3 centimeters, right? And I'm just making up numbers, but this seems plausible. So that would be where the center of the block is. I got to make sure I try to draw it at the center. And so the spring would still do positive work going from here to here. The spring would still do negative work going from here to here, but the amount of negative work that is missing on this side would have been done by friction, because as you're sliding this way, the frictional force would point that way, and the friction would do some negative work the entire time. The spring would do some positive work, then some negative, and the total of all three of those would be 0. Is that still good?
Yeah, so even though the distance isn't the same, it's still net 0 because of the work done by friction.
Exactly. So now check this out. You could do this problem, take a spring, pull it, and then see how far the mass goes. You could watch it with the video. You could get the distances. You'd know the spring constant because you could measure that in the lab. And you could use this as a technique to figure out the coefficient of kinetic friction, which could be very difficult to measure in some other ways. So here's you just designed a problem that I should put on the final exam, if I remember, that would be a very simple way to determine the coefficient of friction. There's no initial kinetic energy. There's no final kinetic energy. We know all the work's done because we can do a little FBD. Done. That's kind of a cool application of that problem you proposed. Is that good, Alonzo?
Yeah.
Very interesting. Other questions? So, yeah, this is pretty cool. We don't have to do any kinematics. We don't have to plot VT. It's pretty cool. All right. Although we'd probably do all that to confirm. Let me see what else we've got here. All right. So, I have a watch out. Watch out. So if we are doing problems with horizontal springs, you could use the words equilibrium and unstretched interchangeably. So think about it. This one right now, we're at the unstretched position. There's a normal force up. There's mg down. What's the spring force when the spring isn't stretched? 0. And so notice the unstretched position is also equilibrium. But that is not true if you do a problem on an angle. Any kind of problem where there's a vertical component. Imagine we have something here. There's a spring. And it's sitting there. Now you hang a weight on it. We know immediately it's going to get stretched and come to equilibrium eventually. And so we see that this up here is x un. And this would be x equilibrium. And so when we're doing springs which have a vertical component, things are very, very different. So Just be aware of that. In general, it's probably best to use the word unstretched for the 0 position, not the word equilibrium, even though that works for horizontal mass springs. All right. And again, why are we talking about springs? They're so useful, right? In springs, there's all kinds of springs, but they all have similar equations. Like a garage door opener uses a large spring and it's coiled. It's a torsion spring, right? Or there's leaf springs. You could use shocks on your car. And like almost anything that vibrates, you could model it as having some kind of negative restoring force, and you could model things as a spring, even if they aren't springs, and you could analyze things and learn about them. So that's a very useful thing about springs. All right. We'll study springs more in the next chapter as well, okay? Now, I just want to point out 7.7. You could imagine you take some crazy physics equation like this, right? And you could say this is a model for a bullet in a gun, and we could model this. It doesn't have to be a good model, and in fact, it's not, but this is one that's doable for students. So here's an application kind of foreshadowing a way this might be useful. If you had some complicated equation for the force, right? This might make sense because first, the explosion is causing a positive force in the x direction, but then as it expands, the x squared term dominates, and the x squared term could talk about maybe air resistance or something. And this model, again, is very goofy. It's not a good one, but it might give you an approximately correct numbers if you put in numbers. So let me just leave it at that. Now, here's the thing. Why would we do this? We could use this to figure out the longest barrel to use for a gun before the force starts becoming negative. So if you use a really long barrel of a gun, is that good or bad? Usually that's good because the air is expanding longer, it exerts force longer. But again, at some point, what if the air expansion is negligible and you get this drag term that's causing a negative force? Well, at that point, maybe we should cut the barrel off so the bullet comes out and it stops slowing down. So this might give you, again, this model is not great. It's just an idea to help you think about it, and it's easy. Here's another one. Imagine you have an electron trapped in some structure, okay? Now, this is a little goofy as well. All these problems, 7.7 and 7.8 are goofy, but I'm trying to give you an idea of how this might actually be applicable, even though these particular ones are completely fictional. So again, this particular one is purely fictional, but it is doable for you. And these relate to similar problems that you might see later. And then some boring talk about quantum dots. If you want, you can read about this. So that's kind of cool. I guess they're coming out with some new solar cells that are going to have quantum dots soon. So that's kind of cool. That's what I worked on back in grad school. All right. This is a good spot to stop and see. Any questions so far? All right. Well, we're actually running a little bit ahead of schedule because in the last class, they asked about 3-4 questions about chapter 6. So I say what we do is we look at another problem. Let's look at either 7.7 or 7.8. Does anybody care? Let me bring them back up.
7.8 just looks cool, so.
All right, let's check it out. So it's very, and to be honest, that's probably a good choice because this one looks a little bit easier for you to do at home, right? Or without me. So that's a good choice. Let's do 7.8. And all right, so I'm going to start by writing this crap down, and I'll catch up with you in a sec here. Okay. Got it. All right. So we have this situation, and this is just another way of writing f subscript x, right? It's a force in one dimension. So this is f of x, f sub x. We're seeing different ways. I hope you see that I'm writing it in different ways and trying to show you they're all the same thing. So if I try to get the units, all right, any ideas? Which one looks easier to start with? Would you try to get the units of x or beta, or I mean, I guess x we know, alpha or beta?
Alpha, so we can cancel out the meters.
Interesting. Okay, but so if that cancels out, what do you get on the basement? It's hard to tell right away. Agreed?
Yeah.
So that was a good thought. And I think that indicates we should probably start with beta, because if we do that, we could cancel out the meters. I get newtons per meter, but I don't know what this is. So how do I get the units of this?
Can we move beta to the other side? No.
I'm going to call it the apples to apples. Oh, go ahead, Alonzo. What were you going to say?
I was gonna say they're both squared, so there might be like an identity for it.
No, they're added together. If you're going to add two things together, what has to be true about their units?
The same.
Yeah. That's where I would go. That's a lot easier, right? So what are the units of beta?
Meters?
Yep. Isn't that sweet? So checking units, I know all the time you're like, that's so easy. This one throws people for a loop. That's why I threw it in there. All right. So now that helps. So now Alonzo, what do we get up top now?
Just newtons.
Yep, we got newtons here. Alpha x, what's on the basement of the fraction then?
Meters.
Squared.
Squared, yeah.
Yeah. So now we could kind of flip this stuff around. This gives me a meters. So what are the units of alpha? We got newtons here. We've got a meters in the basement. It's a real gem of a unit right there. Newton meters. Cool. Unit check can be non-trivial sometimes. Watch out. I'm going to pause and make sure everybody's good with that. Take a sip of water and then I'll go on. Isn't it torturous how almost every physics question feels like there's a unique trick? It goes away after a while, but not right away. Not for a long time. Maybe after week 10. Well, no, maybe after like year 10. But yeah, okay. So we know I'm going to write down the answers to that. Now you may be saying, why am I even wasting my time? Why don't I just do the problem? Remember, we're going to do the problem. And at the end of the problem, usually you do what to check your answer?
Check units.
Mm-hmm.
How could you check the units at the end if we don't know what the units are at the beginning? So this is you're going to see me do this for years. I'm going to do this to you. I'm going to stick these problems in. I'll give you some constants. And part A is going to be check the units so that you know how to check the units at the end. All right. So you might as well get used to writing these brackets the way I like it and this and that, because we got at least 9 more months together, because you got to take Physics 163 with me. All right. All right. So let's go to part B now. What are we supposed to do? Okay. Supposed to get the work in going from 0 to L. What goes inside the integral?
The alpha x over beta squared plus x squared.
Yep. How would you attack this one?
Can you separate the integrals?
I'm sorry, I couldn't hear you there, Alonzo. What was that?
Can you separate them? Integrals? Alpha and x?
By separate.
Like the integral from 0 to L, and then have alpha over b squared plus x squared?
Nope,
Well,
nope. Because that, right? Because that would be, you're thinking like do a partial fractions maybe or something. Yeah, that's not a good idea. And we can't just say alpha. We can't just do this, right? That doesn't work because that would, right? If we had like numbers in there, you'd be like, you can't do that. So while that would be nice, we can't do it. What else?
Just the quotient rule, right?
What's that?
Or
Quotient rule, huh?
where you do what, the low d high minus high d low over thingy.
Well, that's okay. So maybe that's, yeah, I don't know. But when I hear that, I think of taking derivatives with the quotient rule. I think of quotient rule as a derivative rule.
Oh yeah, I'm dumb. That is
No,
not an
it's-
integral rule.
Well, no, that's fine. What else? What would you do?
You
Oh,
sub?
you sub?
Yeah. What's the choice of you might try first?
X squared?
Okay, I would even go this way, dude. I'd say u is equal to x squared plus beta squared. Why not clean up the whole basement? All right, so when I do that, what's du?
Two x dx.
2x dx. And notice we've got an x dx right here. That's cool. You could do it that way. What's another way you could do it?
Integration by parts.
Okay, probably. What's another way? Let me remind you, this is ERT mode in the class.
Wolfram alpha.
Yes. Why would you ever do this if you don't have to, right? So I know this is the thing. You guys all did exactly what we would want you to do in an in-person class. But remember, the real world is your oyster now with this ERT in terms of, I have told you it is legal to use Wolfram Alpha on your test, and I'm fine with that. Because in the real world, you would get to use that. So do the U sub, make sure you could do a little math, then check it with Wolfram Alpha. Now, here's the thing. It's not easy to use Wolfram Alpha when you first start, or any of these symbolic programs, because there's idiosyncrasies involved in using them. But the sooner you start messing around with them, the sooner you get used to that, what you can get away with and what you can't, what the program is willing to recognize and what it won't. So the sooner you start doing this stuff and checking your work with that, this is a huge positive in your career, because no one ever wants to do this, except for maybe me, because I did it in the solution. So let's take a look and see if there's anything in there. But at this point, it's all just boring. All right, just math. Oh, yeah. So here's when I do U subs, students don't like the way I do U subs, but I can't help it if they're crazy, right? Once you get used to this style, you are going to love it. And I always do my U subs this way. So generally speaking, there was only one I didn't do, and it was in that weird one I stuck you with the T-1 in the denominator from chapter 2 at the end or something, or no, it was chapter 4, where we had to get the velocity and the zero limit mattered. Generally speaking, what I do is when you figure out your expression for U, I also just change the limits. By plugging in this into there, you could change the upper limit to beta squared, and you could change the lower limit to beta squared plus L squared. So when you plug in initial and final, you just use these limits over here on the right side, and then you don't have to back sub. So that's how you could just skip a step. And this is also good because it forces you to check and understand your U sub and see if it makes sense physically. So for a physicist, plugging in, changing the limits as well, not just doing the U sub, can be a very useful process. That said, could you just go into here, plug in this equation and back sub? Sure. And that's fine. It's just not, I don't know. I just like it. And like I said, it forces me to think about what U means. Okay. So, I just busted myself. Did you notice you cannot ignore the x initial equals 0 limit? Oh, yeah. When you stick in x equals 0, you get this. And so notice by plugging this into the equation, I don't screw up the x initial equals 0 limit. A lot of you might have just said, oh, I'll just stick in 0. All right. Anyways, enough said on that. I'll pause for questions here while I take a sip of water.
What did you mean by ignore the? How people usually just don't subtract because it's 0?
Yeah, people for some reason, whenever the bottom limit of an integral is 0, they think, oh, I'll just leave off that term and only stick in the upper limit. And it makes me want to like strangle a cat. So yeah, it's like sometimes that 0 limit matters. Gee, I wonder if that is going to show up at some point in the rest of this class where the 0 limit matters. Yes. So I know I've already designed a question on some assignment somewhere. I don't remember which one now, but one of these, it shows up where you have to get the 0 limit in there. It's been in your homework twice now, in lecture twice. So always check both the 0 limit and the upper limit anytime you're doing integrals. Enough said. Other thoughts? All right. So the other one is a little bit easier to do. Polynomials, the 0 limit doesn't matter, but non-polynomials always check it. So like I said, this problem where it's a polynomial, the 0 limit doesn't matter. This one, it's not a polynomial. Don't just think you can ignore the 0 limit. All right. As Christopher Walken once said in a James Bond movie, more power, more power. So whatever that means to you, I don't know. But we're going to probably pick up here next time. But before we do that, I'm going to talk a little bit about the units. All right. So now let's just do this. I like it better on the whiteboard if I can. A whiteboard addict. Okay. So in this case, power, I usually draw it as like a bubbly P, just because P is going to be momentum. Rho is going to be density. Capital P is going to be pressure. So bubbly P is power. Do you have to do this? No, but I'm just telling you why I write my letter P's differently. And this P looks kind of crappy. There, that looks a little bit better. So notice it's, by the way, there might be equations, especially in 162, where all three of these P's appear in the same equation. Not joking. All right. So you got to learn how to write the letters correctly. I know that seems silly, but it is worth putting some effort into. Okay. Question?
Yeah. Is momentum just a normal P, or is that a...
Yes. Momentum is a normal lowercase p.
Okay.
Pressure is a normal uppercase P. Density is rho, the Greek letter rho.
Gotcha.
Okay. So what is power? Okay. So power is, a lot of times you'll hear this, work over time. All right. Now, if you recall, work is something like change in energy over change in time. So this is only approximately true. At any one instant, we say power is dE dt. What are the units of this? Well, let's check. What are the units of work? Do you remember?
Joules? Newton meters?
Joules, right? And what are the units of time? Well, that's just seconds. Joules per second. There's another name for this unit. Does anybody know the name that we usually associate with a joule per second?
What?
What?
I don't. What? Yeah.
What? So bad. Watts. Okay. So the units of power are watts. Now, I had a student in an earlier class ask a great question. They said, what are kilowatt hours? You tell me, what is a kilowatt hour? Let me write it down. Now, you might know, if you ever see your bill on the electric company, they charge you for kilowatt hours, right? So let's figure out what a kilowatt hour is. Well, that's 1,000 joules per second. What's an hour? What's a convenient way to write an hour for this?
3,600 seconds.
So notice it's 3.6 megajoules. Megajoules. So, and the student was like, why do they call it a kilowatt hour instead of a joule? Well, because physicists don't run the world, and we should all be thankful. But it turns out it's very useful to think in this, because this makes cost calculations easier. You think, oh, if I have a device that has this many watts and I want to run it for this amount of time, you could quickly calculate costs from kilowatt hours instead of joules. So that's basically where that's coming from. All right. So that's the units of this. Now, I just want to point out that this is called instantaneous power. And this is average up here. So these equations are not exactly the same. And one time I asked a question on a test that I like, I'm just going to give these people an easy question one time. I'll just give them an average power question so they don't have to do shit. And then turns out everybody screwed it up. I'm like, oh, okay, I should spend more time on average power. So just to clue you in what question that was, I think, this one here. I thought this would be super easy. You give people a car and you figure out it goes from 0 to 20 in 4 seconds, and then it goes from 20 to 40. Oh, looks like I forgot an italics. I should go back and take a point off my presentation. Anyways, you probably caught that right away. Anyways, for some reason I forgot and didn't get those unitalicized. See, it happens to me too. But yes, you've got these two changes. So I thought, well, certainly what a student would think is you just come in here, get the change in energy over change in time, and change in energy over change in time. But then what they did is they averaged those. So in this case, what you could do, well, let's look at 7.12. Take a second to look at this one. Let's take a second. Try to ignore the italics, which is driving me crazy right now. What do you think? What should we do? I'll get this up here higher.
Sh-
How about we write down an equation? What's our one equation that we know here?
So work over power or time?
Yeah, work over time, right? Do we know the time?
For the first stage is 4 seconds, and the second stage is 6 seconds.
Okay. Do we know the work? How do you get the work? How do we get the work? Whoops, I wrote a W there. Excuse me. I was trying to say power is work over time. I'm getting tired.
Delta
so we're
K?
looking,
Whoops.
yeah, force times displacement.
Okay, force times displacement, true, but I like what Jesse said. Delta K is easier. I think that's what you said, right, Jess?
Yes.
And so do we know the initial energy and the final energy?
You know those speeds.
Yep. So, and we know the mass. We got it, right? So this is what I would actually do. I would just say 1/2 m times 40 squared. Now I'm just cheating and leaving off the poorly italicized units here. Divided by 10. That's it, right? We know the total work over the total time. And what students did was they found each stage and averaged them separately, which is not correct. Right? The average power is just go from the initial to the final over the total time and get it done. It's sort of like if you were moving at this speed and then moving at this speed, if this was a VT plot, right? What would you do to get the average speed? Well, first, what you do is you could get the areas and get the total distance, right? So you find the total distance over total time is average speed. So V average is not the average of each stage. V average is total distance over total time, right? Similar thing here, total work over total time. And that got people. Now, to be clear, if the stages have exactly the same time interval, that method would have worked. But in this particular case, because the two time intervals are different lengths, you can't just get each power separately and average them. That would be like saying, I'm going to go at 10 miles an hour for 1 hour and 2 miles an hour for 16,000 years. Clearly, the average speed is not the average of 10 and 2. So, yeah, watch out for that one. All right. And that's going to be our last problem of the day, but let's see if there's anything in the solution since we actually did that one. Where was this one? That was it. 80 kilowatts. And there's the explanation another way if you want. And so that's class for today. I have office hours now. We are going to pick up next time with power and then move on to chapter 8. So if you don't have the workbook yet, oh man, get it. And then tomorrow in class, we're doing exams. You can do chapter 6, whatever you want. And since we have 1 minute, I'm just going to put a quick summary of what we did today. You could leave if you don't want to watch the summary. It doesn't offend me at all. Okay. But I'm just going to kind of think about what did we learn today? Kinetic energy is 1/2 mv squared. We learned about work. It's equal to delta K. We also learned that work is equal to the integral of f sub x dx. Or if it's constant, we can cheat and just say it's f d cosine theta. And we could drink a lot of MGDs when we do forces due to gravity. Okay, so next we could do, we said that the force due to a spring has a magnitude equal to kx, but the force due to a spring vector is negative kx vector. And then we have to remember x un equals 0 if we're going to use that. That was a fact that in order to cheat and get rid of the delta, we're going to use that. We know that work being less than 0 implies trying, maybe not successfully, but trying to slow you. And I'm just going to say it this way. Work being greater than 0 implies you're trying to speed up. And then remember, if force perpendicular to displacement, the work was equal to 0. And so maybe we learned some other stuff, but these are some big points that hopefully you could take with you. And I hope, I don't know, do you guys like it when we at least do some kind of summary or not? If you don't,
Yes.
Okay. Just
Yes.
kind of, that's what we got out of there. And notice I didn't bother to put anything up about power. We'll deal with that next time. All right. So cool. Woof. Get out of here if you want to, or stick around if you want to. Whatever's happening is cool. All right. And remember, tomorrow we're doing practice tests of chapter 6. Anything you want, anything goes. Stop in the live stream.